Who are my... have I got South Korean students? I do.
Who?
Who's South Korean here? Did you say who's South... Okay. Apparently you're South Korean. Did you know this? Yeah. I saw today, no, I don't know, did you see the news? The North Korean leader is going to meet South Korean leader.
Today?
And I don't think today, but today it was said that the two leaders will meet.
Yeah.
Did you see this in the news?
I know.
You know this already? Yeah. That's a big deal, isn't it?
Yeah.
Yeah.
Because the North Korea leader don't have enough money.
Well, this is what I read too, that this is a strategy for North Korea because they have too many restrictions, and this is affecting their money. No, I read this about a year ago, that they were saying they think North Korea is launching all the nuclear weapons so that in the future they can have a meeting so that they can say, we will stop testing nuclear weapons if you please don't restrict our trade so much. This is what you think too, is it? Or?
I think this is a repeated story.
Huh?
Repeated story.
What do you mean?
Yeah, they always threat.
Yeah.
They made a nuclear weapon.
Yes.
Because they said I remade the nuclear weapon to protect
Yes.
the country.
Yes.
But behind the reason is
Yes.
get the money.
Yes, of course. Yeah. Well, this is true for most things in life. The real reason for anything is somebody wants money from something. Yeah. Okay. So for Hooke's law, here's a simple example of Hooke's law. The idea that the more you pull it, the more force that pulls back. That for some materials, the more you stretch it, the more force that you get. This is kind of the basic idea of Hooke's law. So what happens when you pull more on this spring? You get more force. So Hooke came up with a very simple formula for this, what he saw. It's called Hooke's law. And it's the principle that states that the force F needed to extend or compress a spring by a distance x is proportional to that distance. In other words, simply put, as a formula, F is equal to minus kx. Where F is the force, K is the stretchy distance, and K is a constant for the material. And we call the K constant a stiffness constant or a spring constant. X is also usually a small number compared to the total length of the spring. Now, there's a lot here to write this down. You don't need to write all of it down, but you certainly need the formula. So write down what you need to write down.
Why minus kx?
Yeah, I'll explain now why the minus in a moment. Yeah.
If this is one meter,
Yeah.
I stretch this like this 2 meter.
Yeah.
What is this x? This 1?
1 meter. 1 meter. Yeah. X is the extension. Do you know this word? Extension?
Yeah.
Yeah. Okay. Let me know when you're ready. Ready? Not ready over there. Okay. Ready? Continue? Okay. So just to explain a little bit about the picture here. So this is what you have. You have some spring, okay, and then you extend it some distance x, and the x is only here to here, okay. and the force that the spring pulls back is equal to minus kx. And the only reason for the minus is because it's just to show that it's in the opposite direction to the x. So here the x is a positive because you pull it to the right. And the minus here is telling us that the force is to the left. That, in other words, the force will be, it's called an opposing force. Opposing meaning opposite. It acts opposite to what you're trying to move it to. Do you understand that? Yeah. Oh, and the units for K, you might be able to see what the units for K are. Can you see what the units for K are? Think about what the units for F and X are. Yeah, K is Newton per meter. Okay, Newton per meter for the K. Continue. So, I think you probably know this already. I mean, you could probably guess what this means, but the natural length, what would you say that is? The natural length.
Original length?
Like original length, isn't it? The length before it's extended. So the natural length L of a material is the length at which the material tends to return to. It's the length it wants to be at. Or as you said, the original length. It's the length before you extend it as well. That is, so I've realised I've said it 3 different ways now. That is, it's the length it wants to be at. Now, you don't have to write all of those down, okay? I'm just really trying to explain it. So write whichever sentence down you prefer. I think you all were thinking the length before it extends, the original length. That's probably what you might want to write. Oh, no, because I've just said the same thing 3 different ways here, so just pick one of them. Got that? Yeah.
We just use this formula for the French.
No, actually, you can use it for a lot of things. I'm just using spring at the moment because that's the easiest picture in your mind. But there's actually many different materials that behave like this. Continue? Yeah. So, again, I think this is a word you might already know, but just in case, the extension means what? Yeah, but you can't really write this down in your notebook. So, what's another word for extension, or how can we say it? Extension is? Yeah, like a stretch. Anything else? Yeah. So let's see what I wrote down. But you have the right idea. The extension of material is the length at which the material is extended beyond its natural length. So in other words, it's the increased or the extra length past the natural length. You don't count the natural length. It's the additional length. That's called the extension. Please note I use the letter X, but sometimes I might use delta X, or some books might use delta X. And some books even disgustingly use the letter E for extension, which I don't like because we already use E in maths to mean something else. So I will use X or delta X for extension. That is the X. What's wrong with you? No, something's wrong with you. What's wrong? If you're thinking something and you're thinking, should I ask them? Go ahead, ask me. What is it?
Should I write that?
I knew it. No, you don't need to write that is the X. It's okay. Usually small. Alright, continue. So, next. Let's have a look at what this graph represents. So here I have extension and here I have force. What would the slope represent here? The constant. Which constant would it be? It should be the K, shouldn't it? Yeah. Now, there might be other things on this graph as well. So let's see if the area represents anything, okay? So let's just draw the graph here. Yeah, so here, why is there zero force here when the extension is 0? Well, because Hooke said the force is proportional to the extension. If there's no extension, then there's no force. Okay, so as you increase the x, you get more force. And if I don't worry about the minus right now, I just care about the size, then you can see that f over x is equal to k, which is actually the slope of this graph, isn't it? So you can have the slope is k. Now I should also point out, it's fine if you do the graph the other way too. Like sometimes you might see graphs where the f is here and the x is here. If you do have that, then the slope is not k anymore. What's the slope? 1 over k. And you know, it depends how the story is. Like in this graph here, what's happening is you're changing the x and you're looking at what the f is. Whereas in this graph here, you're changing the f and then you're seeing what extension you get. So I mean, both are fine. It depends what way you want to think about it. Just be careful with the slope. But let's examine if the area represents anything. So let's have a look at this, the area here. So what would be good is if we look at what the units are. So the area is of units, well, the area would have the base by the height. So what units is the base? Meters, and the height? Newton. So the unit is Newton meters. But Newton meters is a special unit. You've seen this somewhere before. Does anyone remember what the Newton meter is? Ah, that's Newton per meter squared, is Pascal's. Joules, yeah. A joule is a Newton meter. And what do we use to measure, or what do we use joules for? To measure what? Energy or work, yeah. So, what do you think this area might represent for the spring if the units are measuring something that we think is a work? Like, what work could it be? Not kinetic. Not potential. Well, kind of not potential. That's something else. I'm not asking about the energy, I'm asking about the work. What work was done? Pulling the spring. Yeah. So in other words, the area represents the work done to go from no extension to whatever this extension is. So the area from A to B, and let's call this A and let's call this B. In this example, A is 0 and B is whatever. The area from A to B is equal to the work done in extending from X equals A to B. So if you want to know how much work is involved, then you can calculate this. And you realize, oh, it's not so difficult. I can actually get a formula here because in this example here, it's just a triangle. So what's the area of the triangle here? It's a half the base, which in this case we can just call it x. We can call here to here x. And what's the height? The height is f. But we have a formula for f. What's the formula for f? Kx. So a half k x squared. That can be the formula for work for the spring. And Bruce, another way to say this is a half kx squared is the formula for potential energy for the spring. So what you're doing is when you pull the spring, you're doing work, and the work you're doing is putting energy in the spring, because now when you let go, this energy comes out. So the work done is putting potential energy into the spring by extending it. So what you need to write down is this result and this result here. And I think it's good if you can have both graphs with the two different slopes. Got that? Continue? No problem. Can you see? Yeah. Continue now? Yep. Okay, great. So we've talked about this already. The energy stored in the spring by extending the distance x past its natural length is given by the formula, which is cut off my screen for some reason, but we wrote it down. Now, in this graph, I put the extension here and the force here, because for this particular experiment, if I can draw it for you, what would be normal to do is you would have some material. Well, I'll draw it as a spring. Hang on, let's try that spring again. And then at the this we could say is the natural length. And then you come along and put a little hook here. And this here measures the force in newtons. Force in newtons. You've probably seen these before. You pull them and there's a little... have you seen these before? I have one in the office. I'll bring it to class next time. But you just... You hook it and you can pull, and then you can see what force you're pulling at. Yeah. So you can measure the force, and then this force will cause an extension. So you change the force, and then you measure the extension. So that's why the I screwed that up, didn't I? Because I want the extension down below. Oh yeah, sorry. You pull it. You cause the extension. And then you measure what force you see by that extension. Anyways, it doesn't really matter. I screwed up that explanation. But the important thing is that the extension is here and the force is here. In real life, the graph isn't a straight line. I mean, it would be a straight line, but then at some point, it's no longer a straight line. It starts to curve then. And this is because materials that are stretchy are only stretchy until a certain point. And then if you try to pull it past that point, it's no longer as stretchy. Now you can kind of picture this with the spring. So if you have a spring and you stretch it, you realize, oh, if I stretch it too much, then it's linear, it loses its stretchiness. And this is true for every material. Like with my sweater, you see it's stretchy. If I pull it and let go, it snaps back. But if I actually pull it enough, then it loses its stretchiness, and it won't snap back anymore. So that point on the graph is called the elastic limit. That is the point at which Hooke's law stops. Now, what's not on this graph, which I want to add into the graph, this part of the graph obeys Hooke's law, and this part, Hooke's law, is not true. We call this part of the graph the elastic region. And this part is called, does anybody know the opposite of elastic?
Inelastic.
I see, he said the right one. I was hoping to get more people tricked into saying inelastic. Yeah, no, I got you, yeah, but this fella knows it. What's the opposite of elastic? Plastic, yeah. Plastic region. Very good. Yes?
Plastic region is flat?
The graph?
Yeah.
No, it could be a curve. Or it could be flat, but it's usually a curve. I think probably what would happen in real life is it's flat and then it maybe curves a little bit and then goes flat. Yeah, but in the exam, you don't actually draw much after this. You kind of stop it soon. So this part is the elastic region, and this part is the plastic region. Now, I've seen them ask this to draw this in the exam a couple of times. They ask you to draw it and to label the regions. Yes. Sleepy Bruce?
Yeah.
Yes. Can you draw this, please?
Yeah.
Okay. And this is elastic and this is plastic. How did you know that was called plastic? Did you learn this in school? Or you're just a genius? No, it can't be a genius. Did you learn it in school?
High school.
High school, okay. What's going on? You knew it was plastic as well?
Why is it called plastic instead of inelastic?
It's a very simple reason. The reason is English is stupid. Yeah.
This is a good reason.
You think it's a good reason? Okay. English is a very bad language for rules. Like other languages will be better for rules. Like if it's elastic, then it should only be called inelastic. Whereas English, you have so many exceptions. So I don't actually know. I'm sure if you ask an English teacher, there might be an interesting reason why it's called plastic, but it's certainly not an important reason. Yeah. You see, it's probably, it's probably something really stupid like, oh, well, it's elastic, and that comes from the French. And in French, the opposite of whatever elastic is plastic or something. I don't know. It could be some stupid reason like that. That its origins is that it's not an English word. Okay, we got that. Yep. Continuing. Right. So just some terms to be clear. We have elastic, which is where the material follows Hooke's law. We have plastic, which is when it no longer follows Hooke's law. And we have elastic limit. What would we say the elastic limit is? What might you say? Yeah, it's the point at which it switches from being elastic to plastic. So it's the point when it's no longer elastic and becomes plastic. I think it would be good to write these three terms down, please. Just to go back about the plastic and the inelastic, I think actually the difference the word inelastic actually does have a meaning. It is a real word. Huh? Inelastic? Yeah, I think it has a meaning. I think the difference between inelastic and plastic, I think plastic means not elastic, but you can still change the shape. Whereas inelastic, I think, means not elastic, but you can't change the shape. So, for example, if I pull this and it's not elastic, I can still change the shape afterwards, even if it's not stretchy. I can still like bend it or move it or whatever. It just doesn't stretch back. So I think the small difference between inelastic and plastic is when you use the word plastic, you're saying it's not elastic, but I can still adjust the shape. Yeah. I don't know. You'd have to check the dictionary for the word inelastic to see what the meaning is. Actually, I don't mind if you want to check now, because I'm actually curious what is the exact meaning of inelastic, if it's the same thing as plastic. I can just tell you for the exam they want the word plastic for the exam. Now, if the definition is stupid, don't break my heart and tell me it, okay? If it's something like, I don't know. Inelastic means not elastic, but delicious.
It should be less elastic.
Less elastic, yeah. Or anti-elastic, unelastic.
In business, graphs are like elastic and like this, and elastic is something else.
Yeah, you have, in economics you have elasticity and elastic and inelastic, yeah. But when you're describing materials and not graphs, you talk about material being plastic. Have we got the word inelastic? Come on, make me happy now. What's the definition? You got it? Go on, read it to me. Make me happy.
Not elastic.
Ah, that. I'm so not happy with that. Has anyone else got a better definition? What have you got over there for inelastic?
It's from another person, which
Yeah.
says inelastic is stress, strain curve is not linear. Plastic is relatively stable, strain remains after unload.
I don't like that definition. Alright, continuing anyways. In the exam, please use the word plastic. That's what they want for a mark. Okay. A mass M is hung to an elastic material which is suspended from the ceiling. Or maybe the mass sits on top of a spring. In both cases, the situation is actually the same. So, imagine we have something on the ceiling, and we have a spring, and this hangs at the end of the spring, or maybe it's like this, and this hangs here, or maybe it's on the ground, and it hangs like that. So, this one is going up, down, this one's going left, right, this one's going up, down. In fact, for the next formula, you can use the next formula for all these situations. Okay, I'm not going to do the proof of this formula. I don't know why I used to do it. It's really, really long and not necessary. But for all these formulas, you can actually calculate the time, the periodic time. Not only that, I should tell you, the motion here, this up, down motion, or left, right. We've seen this before in the last chapter. What motion is this? This left, right, up, down. What's that motion called? Periodic, yeah. And what was the name of the lesson? Simple harmonic motion, yeah. So you can use your simple harmonic motion formulas for the motion of a spring. But the problem with that is that sometimes it's hard to work out things like the omega, because when we think about a spring, the things we know are the mass, yes, we can easily know that, and we can easily know the K for the spring. So, is there a formula that instead uses M and K? Because in simple harmonic motion, the formula was 2 pi over omega, wasn't it? But we don't know what the omega is, we can only know what the M and the K is. So the good news is there is a formula, and here it is here. it's 2 pi root m over k. So you can use this formula to get the t. And what's really nice is you can then also use this formula, and if you put these together, what could you know? You could know the omega. So this is a very useful formula for springes and circular motion, simple harmonic motion caused by materials that obey Hooke's law. Yeah? You got that formula? Yeah.
Time.
Periodic time, yeah.
Is our physics exam before or after holidays?
I have no idea.
Just guess.
Just to guess. Well, I can tell you what it was supposed to be before. But I feel like because we lost time to the funeral and to the snow and all the stuff that happened recently, I would feel like a lot of the teachers now need it to be after the break because of the time. So I haven't heard what the principal's plan is. It's supposed to be before the break, but it would not surprise me if she changed it to after the break. We'll see what the other teachers think.
So holiday will be studying.
Oh no, your whole life is study right now. Not just the holiday. Okay, continue. Yep. Now, tell me what would happen to the time if I do this. So, I pull this down and it starts moving. What about if I pull it down even more, let go, and it starts moving? Which has the greater time? The t is bigger for which one? It's the same, correct, yeah. The t does not change because in both these pictures, yeah, true, the a is different. Well, that's a bad picture because I need to scroll down. But anyways, this formula does not have an amplitude in it, which means it doesn't matter how much you pull it down. The time is the same, which is quite interesting because you might think, oh, if I pull the spring really far and let go, I'll make the t bigger, but you actually don't. The only thing that affects the t is the mass and the k. It is not affected by how much you pull it down and release, which is maybe surprising, but I think it's worth saying that. This is a bit like in the pendulum formula. The pendulum formula is not affected by your initial amplitude. In the you remember, it only cares about what in the pendulum formula? The length, that's all. In fact, it didn't even care about the mass. But this one does care about the mass. Okay. Right. So here's a very simple one which I think you can do to start. A rubber band, do you know what a rubber band is? Does anybody have one? Yes, you might even have some in your hair right now. Yes, possibly? Yeah. No. Well, I suppose you don't need to if you have the headscarves on, right? Yeah, it's not necessary. You know a rubber band? Bruce, do you know a rubber band? You have a rubber band in your hair, don't you, at the back? It's the same thing! The thing in the hair, you stretch, okay? Like this. So you have a rubber band and its natural length is 10 centimeters and its constant is K. And the K is 1 Newton per meter. So you pull the rubber band so it's twice as long. What is the force? Okay, so what formula do we use? F equals Kx. What's the K here? 1. And what's the X? 0.1. Yeah, because it should be in meters. So what's the F? 0.1 newtons. Yeah. Okay, so yeah, negative. But I suppose if I'm going to be technical about the English, because I said how much force and not what is the force, I don't need the minus, because how much means size, and size you don't care about sign. So not necessary for the minus.
But I have minus in the right.
If you wrote minus, I'll still give you the mark. Yeah. Okay, continue. Yeah. Right, a spring is hanging from the ceiling and you stick a 2 kilogram weight on it. And this causes the spring to extend by 5 centimeters. What is the K? So just so you can be clear, here's the picture. Here's a spring, and then you come along and stick on it 2 kg. And of course what will happen? It will stretch down. And this distance here is 5 centimeters. So my question is, what is the K? Now what could we do to get the K here?
Which
What?
one?
Yeah.
4.5.
Well, I'll just help you out. In this picture it's not moving, okay? You carefully put the weight on it and it slowly falls down and stops. So if this is not moving, what can we say? Newton's first law.
Is it constant?
The other half of the first law.
That is
No, that's the second law. If the object's at rest, then what do we know about the force? It's an equilibrium, there's no net force. So the force here should equal the weight. Now what is the weight? 2g. And what is this force? Well, that's Hooke's law, isn't it? The K, which we don't know, and what's the X here? 0.05. So if I just divide, I have, what's that, 19.82? Is it? Yeah, 19.82 over 0.05. That's 2024. Is it like 398 or something? It's close for a gut instinct answer. What is it? 392 newtons per 392 newtons per meter is the K. Is that okay? Yep. Next example.
Why isn't this negative?
Because the K is never negative, because the minus is in the formula, not in the K. So you shouldn't have the K minus as well, because the minus is in the formula. And the reason I don't need the minus here is because I'm saying up equals down. So I already have the minus in the picture rather than in the formula. If you really wanted to use a minus, you would have to do it like this. You would have to say 2g minus 0.05k in total is 0 newtons. Continue? Yeah? Yeah? Okay, so a spring with constant of 2 is attached to a wall. A boy pulls at a distance of 10 centimeters. How much work was done by the boy? So how much work did he do? Well, what formula do we need here? A half k x squared. Do we know the k?
Yeah.
Yeah, do we know the x?
Yeah.
There it is, so calculate it there for me.
0.1. No. 1.
A half times 2 times, so 0.01 joules. So the boy did 10 millijoules of work. Yeah. Continue. Yeah. Okay. A rubber band is attached to the ceiling. A 100 gram weight is hung on the rubber band and extends the distance of 5 centimeters. The weight is pulled down a further 4 centimeters and released. How long until the weight reaches the maximum height? Okay, so let me draw the story here. Here is the ceiling. Here is the rubber band. Then what happens is you put on a 100 gram weight. 100 grams, not 100 G. And that causes it to move 5 centimeters. Then someone comes along and pulls it down another 4 centimeters. And that pulling down, it will cause it to move in a simple harmonic motion. Okay. No, actually, I'm sorry. I drew that wrong. It's like this now. Okay. So my question is, how long will it take to go from here to up here? My question is, what is the time to go from here, the bottom, to the top? Okay, now this is quite hard, but if you do it in steps, it's not so bad. What can we know from going from picture 1 to picture 2? What can we learn from going from picture 1 to picture 2? We can get the spring constant, the K. Yeah. So because in this picture it's in equilibrium, it's not moving. It doesn't move until someone pulls it down and releases. So here, this F will equal the weight. So you have F, which is Kx, equals the weight, which is mg. So the K will be 0.1 times 9.81, so that's 0.981 over 0.05. 90.62? 19.62. Now when we go from picture 2 to picture 3, in picture 3 it's moving in simple harmonic motion. So what formula could I use? The T one. T is 2 pi root m over K. Right, so what do we get here? Now, that is not the answer, because that is the time to go up and down. And we only want the time to go from the bottom to the top. So, what do I do to this answer? So divide by 2, and what do I get?
0.224.
And that's the answer. Can't hear you with the motorcycle. Speak up, what? Because my question was, what's the time to go from here to here? That T is for one oscillation. So if it starts here, that T is for getting back to the start. It's like for one loop. Yeah.
So the first Fourier difference will be second Fourier time.
No. Same time. Well, in real life, it's not, because it's slowing down. But for our physics, we keep it simple and say it's the same. Yeah. But in real life, it's changing. Yeah? Got that? I've seen this in the exam. It's kind of hard, but then at the same time, it's not so hard if you know what to do. But if you didn't know what to do, then it seems quite hard. But when you look at what I didn't really do much. So it's kind of one of those questions where it's hard only if you haven't seen it before. Then it's actually easy. Yeah. Okay, continue. So I think that was the last example. Yeah. And I think we're finished there. Yeah. Are you in this room next? No. Okay, so we'll finish that. We're in CAV later, aren't we? Yeah. Did you bring your laptops? No.